Lesson number 4. Yes, it was the inventor of the telescope, Galileo Galilei, who observed falling objects and came up with his law of falling bodies in 1638. Let's learn more about it. Here's your challenge. Can you describe the motion of the car down the road? Ready, set, go. Of course, from previous videos, you've seen that car is accelerating. So that horizontal motion along the road is accelerated motion. But what if we took that car and placed it over here in the sky? What if we had the car fall and drop to the ground? How would it fall? Well, you might have two choices here. You might think that the car falls at a constant speed and is just going to fall from the sky to the ground at a constant velocity. Or you might think if you drop the car will fall and gradually get faster and faster and faster and accelerate. This accelerated motion is what Galileo observed, and let's see how he described it. It was in the 1630s when Galileo dropped objects off the infamous Leaning Tower of Pisa. Let's drop a tennis ball off there now. Ready, go. As you can see, the tennis ball accelerated. Let's chart its position relative to time as it fell. So let's say the tennis ball started right here, and we'll call that time 0. After the first time interval, not necessarily 1 second, the tennis ball was here. After the second time interval, the tennis ball was here. And after the third time interval, the tennis ball is where it is now. So let's look at the distance it fell. Well, Galileo noticed that it fell 1 unit of distance in the first time interval. He then noticed it fell 3 additional units in the second time interval. He then noticed it fell 5 additional units in that third time interval. Let's total it up and see how far it fell each interval. So after the first time interval, it fell a total distance of 1 unit. After the second time interval, it fell 1 unit plus 3 more for a total of 4 units of distance. After the third time interval, it fell 1 plus 3 plus the 5 units for a grand total of 9 units of distance. Thus, Galileo recognized that the distance the object falls is proportional to time squared. Because if we look, we can see, well, after the first time interval, 1 unit of distance. After the second time interval, 2 squared, that's 4 units of distance. After the third time interval, well, 3 squared is 9 units of distance. And you can see that's related directly to the equation we came up with earlier, where distance equals 1/2 acceleration times time squared. So the question now is, what is this acceleration rate due to gravity? Freefall, how fast? Let's drop the tennis ball again and observe its motion. Ready, go. So from the last video, we charted its position. So let's say it starts here, the next time interval was here, next time interval it's here, and then that third time interval is right here. Well, Galileo went to measure what the speed of the ball was at each time interval. He saw the speed increased as it fell, but in the negative direction, in the downward direction. So we'll call this way downward our negative direction. He approximated that since the initial velocity was 0, the next velocity was about 9.8 meters per second, but in the downward direction, so negative. The next speed was 19.6 meters per second, or negative since it's in the downward direction. And that last speed was 29.4 meters per second, or negative since it was in the downward direction. You notice that the change in velocity is negative 9.8 meters per second every second that goes by. So that tells us the acceleration is negative 9.8 meters per second squared. And that's specifically the acceleration due to gravity. So for any free fall problem that we do, you will always know the acceleration due to gravity of that object is negative 9.8 meters per second squared. You just learned that dropping a ball through the air is in free fall. But what about throwing a ball upwards into the air? It turns out that ball is also in free fall because gravity is the only force acting on it. Let's take a look as I throw this orange ball into the air. Ready, go. As you can see, the ball accelerates when it leaves my hand at the rate of gravity, which is negative 9.8 meters per second each second. That means that gravity changes the velocity of the ball by negative 9.8 meters per second every second it's in the air. Let's sketch the path of the ball through the air. So here the ball leaves my hand, it's going up, up, up into the air. It reaches its peak and then comes straight back down to my hand. Notice I labeled the location of the ball at every second it was in the air. So when it was in my hand, it was time 0. 1 second later, the ball was here. Another second later, the ball was at the peak after 2 seconds. Another second later, the ball was here after 3 seconds. And then the ball landed back in my hand at 4 seconds. What is the velocity of the ball at each of those times? Well, if gravity accelerates the ball and changes its velocity by negative 9.8 meters per second each second, and I threw the ball upwards at positive 19.6 meters per second, we can see that gravity will change that velocity by negative 9.8 meters per second every second, making the velocity decrease from 19.6 to 9.8 meters per second after 1 second. After the next second, I subtract off another 9.8 meters per second of speed, and at the peak, the velocity is 0 then. Another second later, I subtract off negative 9.8 meters per second, and that gives me a velocity now of negative 9.8 meters per second. Another second later, I subtract 9.8 meters per second again, and I get a velocity of negative 19.6 meters per second. Notice that as the ball goes up into the air, the velocities are positive. It reaches a velocity of 0, and as it falls back down, the velocities become negative. This is very similar to when you walked away from the motion detector and your velocities were positive, and you turned to walk back towards the motion detector and your velocities became negative. That positive and negative sign just refers to direction. So as a ball is thrown into the air, its velocity is constantly changing because the gravity is accelerating it constantly at negative 9.8 meters per second squared. Thank you for watching, and see you in class.